Hello, welcome everyone. Thank you for joining us this evening. And thank you, Daniel, for preparing for this event. Today, as most of you already know, we'll be showing you how to make a speech recognition model. You can follow along through the Google Colabs, and the link for it will be shared in the chat right now. I believe you need to go to GitHub repo first, and then you'll be able to find the link for the Google Colabs. As we're going through, Daniel will be showing you each step in real time and explaining what's happening. The terminology should not be too complicated, but if you are unfamiliar with some words or concepts, feel free to write us a question in the chat. We'll try to answer it either during or after the event. As it's more interactive session, you can also ask questions using voice chat, but please do so at the end of the presentation. In that way, we can make sure we don't run over time. This event is recorded, so please be aware of that. The recording will be available on the CT Data Science YouTube channel, and the link for that will be shared with you as well here and in the WhatsApp group. So Daniel is finishing his master's here at City, and you may remember him from the session we did last time, which was detecting fire with AI, which you can also find on our YouTube channel. So let's make a start then. Up to you, Daniel.
Okay, can you hear me?
Yeah, we can hear you.
Cool. So hello everyone. Thanks for turning up. And so we have this link, and all being well, we should be able to see a page similar to share this. Share screen. Screen one. Share. Okay. So all being well, we should be on the City Data Science Society NLP workshop screen. And if you landed on the screen, always good. If you landed on a screen that looks like this, and then we want to click that link NLP workshop, and then that's it, we're here. So can we have a, where are we? Okay, so next thing we do is, well, we'll just go over the problem. We're trying to use this thing called a convolutional neural network to help us identify some element of speech. So we'll look at the basic workflow on how we do make that thing happen, right? So we're going to get a training data set containing audio, and then we're going to run that audio through a neural network, and the neural network that we will train during the workshop will predict if the class is yes or no. So in that case, we have a wave file that looks something like this for a yes. So we can see there's a big bulk here, and then that tail, the sounding yes. And then we have a no file, and we're going to get the signal and pass it on to the neural network and see if it can predict. And most times it can, sometimes it fails, and hopefully we'll see both cases. So if we click on this Open in Colab link, we should land on a Google Colab page, which looks like this. So, right, Max, Ben, I can't see the control screen, so I cannot see, I can only see the screen I'm sharing. So if you guys can give me any audio cues as to what's happening in the background, all good. All right, so there's one latecomer, welcome. I think I missed your name, but we should have a link to this Google Colab in the chat. So if you click on that link, you'll be on a page like this. And if you arrive on that page, we want to click this link here, Open in Colab, and then you'll be joining us on this Jupyter Notebook. So this Jupyter Notebook, if you've never used it, it consists of cells, and the cells can be like mostly we only deal with two cases. A text cell, so it contains text, like this cell here is text, and this one here. And then we have code. So speech recognition with AI, we're using a data set that's supplied by Google, which is called speech commands, blah. And we'll go over this in a sec. Let's get that data first. And so let's run cell 2. So this cell here. So we just click that run button, and what it's going to do, so we can click it, and it's going to say, do you trust this notebook? Run it anyway. So it's going to run these commands in turn. It's going to use wget, which is a Unix/Linux command, to download this file here that comes from Google. So there is, it's downloading. Then it says make a directory called full data set. And then it says, and expand or decompress these files and send them over to the full data set directory we created, and then make a data set subdirectory, and then move all the yes words to the data set, and then move all the no words to that data set subdirectory. So we're going to end up with a data set subdirectory just with yes and no. Now let's go back up here. This while this thing is happening down here. So what this data set is, so was everyone able to run that cell, cell 2? Ben, Max, could we get a show of hands there?
Yes, can you please write in the chat or?
Oh, cool, I can see the chat here, yeah, cool.
Okay.
The talk will be uploaded. So, all right, so I'm gonna assume that it's working for everyone, and we're able to run that cell number 2, and that the data has all been downloaded. So let's have a quick look at what this is. TensorFlow speech commands data sets about 3 to 4 years old now. So what they did was a crowdsourcing exercise. They got thousands of people to record 65,000 words, 3 short words, plus some background noise that also went into the data set. And we're using a subset, yes or no, but the full set consists of 30 words plus the background noise. And here is a list of the words. So the ones we're interested in, and it's called command, the speech command, because it's got a number of like words that you could see as being used as commands, like right and left, up or down, on and off, yes and no, and so forth. So now that we have this data set, I'm just going to close the output if it finished. Yes, it has finished. So I'm just going to close this output, and we're going to have a look at this environment we're in. So we can run some commands. And here I'm going to, on cell 1, I'm going to remove this hash sign from the second line. And so what this is saying is exclamation mark. So run a command on the shell itself, not in this cell, in this as a script in this cell. Run it on the virtual machine that we're on, and each of one of us is on a different virtual machine. So this df.h says display me the amount of space available in human readable format. That's that H switch, and it says you have 34 gig available. That's what interests us. Okay, we have 34 gigabytes available to play with. So, and then we could go and use, there are other commands we could use. So we could ask for help as to what that df command is. And if you've used Linux or some flavor of Linux, this might look familiar to you. You'd say, well, can you show me the manual for this df command? And then it would then print out the manual. And the same for these other commands. So I'll ask for list, pwd for print the working directory. So where are we? And then what's on the root topmost level of this directory? We would run this command there. So there's a link on the chat to this natural language processing workshop. If you click on this open in Colab, you're going to end up on a page like this. And what you need to do when you get there is click on cell 2, get the data. If you hover over it, you're going to get this run icon, click on that run icon, and it will start downloading your data. It should take a minute or two, and you should be at that point up to date with us and able to carry on running the code. So let's move on to this other part here. So we want to see what we have in this data set subdirectory. So we're going to run 3 commands. We're going to list the data set, and we're going to use this symbol here that is the pipe symbol. And we're going to use a command called word count, and we're going to pass it the switch L. That means list me the do me a count of the lines of everything that's coming from the previous command. And it says, okay, from the previous one, when I list this data set, yes, you have 2377. So we have over 2,000 yes recordings. And when we do it for no, we have over 2,000 no recordings. And then when we list the data self itself, the directory, we have a no directory and a yes directory. And the significance of this is that further down, the codes that we use to train actually looks at these directories as category labels. So everything our model finds in this no directory, it's going to say, okay, I know what's going on here. That's a no word. And everything it finds in the yes directory, it's going to say, okay, yeah, because it's in that yes directory, that's a yes word. Right, so the next thing we do is we need to run this cell 3 to import the modules or the libraries that we're going to be using. So we run that guy and nothing's going to happen. There's no output, but we imported the data. So imported the library. So now we can go and visualize some of this data. So we run that guy. And so we use the Librosa library to load these, the sample, the audio file plus the sample rate. And if we hover over it, it will tell us what that file is, what the inputs are. So it says, well, it's expecting a path or a sound file as an input, plus a sampling rate, and as an output, it's going to give you a NumPy array and plus a sample rate. So it's then again, if we hover over that load, it would tell us what that's doing. And then now we have a NumPy array with 8,000 elements, and we have a sample rate, which is 8,000, because we said when you import this thing, make sure you import it at 8,000 kilohertz sample rate. So the next thing it does is it plots that wave. So it plots the wave here, and then we can see by the shape that it looks like it's going to be a yes, right? Because there's that pattern we've seen before. Marlon, have you managed to download that data? Oops, Paula. Okay, Paula, can one of Ben or Ben or Max, could you give Paula a heads up on running that cell 2 and that cell 3, so Paula can get it up to speed with us on this cell 4, please, through the chat.
Yeah, I'll message Paula.
Cool,
to make
thank
sure
you.
she's up to date.
Okay, so here we are on cell 4, and now all being well, if you guys click this guy, you should be able to hear, all being well, that's sample. So could someone confirm, like yes or no? Were you able to hear this audio?
Yeah, you could hear the audio.
Cool. So I am going to take that single sample as a sign that everyone was able to do it. It might be a bit optimistic, but let me know if you haven't, and we'll see. Normally, what would have happened at this point is if this failed, you might have forgotten to run this step 3, because we need a couple of these libraries to actually plot this stuff. So next thing, let's do the same for no. So same thing again. We're going to load a file in the data set, and we're going to the no subdirectory, and we're going to load this file specifically. So I've rummaged through that data set, and I know that there is this file. And same thing again, at sample rate of 8 kilohertz. And the rest is what we did before. We're going to plot it. So we plot it, and we see that familiar kind of pattern. It's kind of bulky, and there's not the S tail we've seen here above. So we run that guy.
No.
And all being well, could someone confirm that you could hear a no there in the chat? Or
yeah, yeah, it was
Yeah,
known for me.
could hear that.
Cool. So now we're going to have a look at these data types. So up here, we know we got an array, and it's saying that it's the array, the ND array, a NumPy array, NumPy being a Python library, is of shape 8000, comma. Not going into details why it's that comma, but basically if we run this, it says it is a NumPy array. That's the class. So we say print the type of samples no, and then we say print samples no dot shape, and it says it's 8000 comma something. Now, what can
So Daniel, is it
Yeah.
just to ask a question here? So, because comparing this to the other workshop we did where we were looking at classifying images,
Yeah.
How would you describe that? How the data's changed here? So, is this a different size of input? Is this a one-dimensional array compared to two, or how would you
That is
compare them?
the main difference. The main difference is we're dealing with a single dimension. It's a one-dimensional array. So we're dealing with audio. In the previous workshop, we were dealing with images, so a two-dimensional array. So we were dealing with 2D before, now we're dealing with 1D.
Mm-hmm. So would that, presumably that means the model will be faster to run, or do you not notice a difference in that sense?
That's totally dependent on the data, how much data you have, how big is your model. It could run quicker or faster depending on those hyper parameters, I'll call them now, and we'll go over that terminology a bit further along.
Okay, cool, cheers.
Cool, thanks. Someone else we have here. So again, could I ask one Max or Ben to go over with Anselm? And
Cool. Yeah, we'll keep an eye on people that are joining and follow up. Cheers.
Cool. So at that point, we would have wanted them to run cells 2, cells 3, and cell 3. So those are the two key cells to run at this point. So where do we go from here? We have these two files. How would we, like if as a software developer say, okay, is there a way we can write an algorithm to say one is a yes, one is a no? If you look at it, you think, well, maybe if you had some way of characterizing this, like statistically. So let's say if we looked at the mean and standard deviation for both these waveforms, we'd see, well, the mean is tiny, and that makes sense because if we look, most of the time, it's kind of symmetrical, and it's almost always close to this 0 level and on this y-axis. So that would make sense. What about standard deviation? And we say, well, the no has a slightly smaller standard deviation than the yes. So in this case, we could say, well, we could get a sample and say which one, if we set a threshold and said, well, what if we set a threshold of 0.047 and said, if the standard deviation is less, we'll say it's a no. And if it's more, we say it's a yes. And that's a perfectly valid approach. It's a statistical approach, right? We're trying to extract a feature here. In this case, we've done it, so a so-called manual feature extraction. And we decided that if the mean was below or above a threshold, the standard deviation will classify that word as a yes or a no. Okay, so that's one way of doing it. That's not the way we're going to do it. We're going to use this neural network. And so, and on we go. This is just to get this, start this discussion on how would you go about doing this with traditional rules-based programming, for instance. If we had to write an algorithm by hand, classify these two words. So next thing we'll do is look at something we've seen already. So what this cell is doing is just showing us the labels. So go to that dataset directory and list the subdirectories in there. And it says you have yes and no. So those are our audio labels. Now, the next thing is we're going to look at where are we? We are visualizing the data, right? So we're in this step 4 here, and we are going to find the count. So this is not, we're not changing the data in any way. We're just looking at it. So if we don't run this, it's not going to impact the outcome. We just want to see what we have. And this is something we've seen already through that list and pipe through WC -L. So get a count and we say, yeah, we have over 2,000 examples, we'll call them, of each case. So of yes and of no. And then let's look at a histogram of the durations. And this same again, this is just to visualize what we have. And here it's saying we have over 4,000 cases where it's 1 second duration. And then you have a few here, not many, that are less than a second. The ones that we're interested in is over a second, is 1 second. And so what we'll do is we're going to get rid of these other cases. So now we're doing a bit of data cleaning. We're going to pre-process the data. So at this point, we do need to run these steps, right? So I'll ask Marlon, Paula, and Anselm, if you guys are all up to speed here and you're good to run this cell 5. So if you've run cells 2 and 3, or they might be still running, but you have time to catch up further along. But hopefully, if you go past those 2, this is the one we need to run next, right? So cell 5. So we click this guy. And what it's going to do, this is the one that takes the longest to run. So what's happening here is we're setting an audio path to say it's date set. We're going to create 2 lists. And then we're going to loop through labels. Now we know what labels is. We've seen it up here. Labels is, one label is yes, one label is no. So the first loop it's going to go through in labels is yes. And then it goes print labels, I print yes, and it says, okay, waves, I define a variable called waves, and I say, we're going to go through all the files in dataset yes. And if it ends with .wav, which is the audio file, go into this next for loop. And then it says, load that file. And then we've seen this already. We've used this load file, and we've seen this part as well. We want it at 8 kilohertz sample rates. And then we go and say, if you have 8,000 samples here, and we can see up here that we would expect them to have about 8,000 samples. Oh, there's a missing link here. I didn't make any mention or correlated the fact that 1 second files do have 8,000 samples. But that's what's going on here. So if it does have that length we're after, append the sample to this list of samples and append the label to this list of labels. So as an end result, we end up at this point, once we've run cell 5, we end up with one list called wave, and then another one called the all underscore labels. And we can see here we have 4,000. By hovering over that label, we can see, okay, the first label is yes, we have 4,255 items in total. If we hover over this other one, it says that's an ND array and so forth. So now here we'll run this cell. It's not essential that we run it. It's just for this, for sanity checking. And it says, yes, you have 4,055. And we hovered over here and it told us the same thing. You had, anyway, I won't wait for it to hover over. It's 4,055. Okay. Now this guy, like this previous cell, we do need to run. So where are we? Is everyone up to this cell, or does anyone need a bit of extra time to get to? So we're running the cell that begins with from sklearn.preprocessing import label and
Looks good so far.
cool. So we run this guy, and what we're doing here is we create a list of, we turn our array labels into a list. and classes. Now this, okay, let's move on to this one. Array dot labels NP utils. Oh, the key thing that's happening here is we are turning this into a categorical label. So what we had before here was, let's run this guy here. So if I run this guy down here, array labels, it's going to tell us what is in, for instance, this element 0. And it says in element 0, you have an array with, you have where you have a list with 0 and 1, a class list, array categorical. Yeah, that's where we are. So it says the first one, which is a yes, the first element is 0, the second element is 1. The last one, so what this thing is doing is print the element, the last element of this array. So it says go to array labels.shape and get me the 0th element. So I'm just going to run a cell here to understand what's going on in this statement. So if we look at array labels.shape, just without this index, if we run this guy.
Sorry, Daniel, can you speak up a little bit to the microphone? I think you lost.
Okay, sorry. Okay.
Thanks. I think it's better.
Okay, Hyundai, welcome to the workshop. So there's a link there to the City Data Science Society page. There's an Open in Colab link, which you would need to click. And then once you get to that Open in Colab, you need to run cells 2, 3, and 5. And once you've run cell 5, you also need to run the following cells after it. And if you keep running those cells, you catch up with us. We're just after 5. It should take about 5 minutes to run those cells, and then you should be up to speed. So continuing, what's this thing doing? It's saying, go to the last element of that array, give me the 0th element. So it says, what's the shape of this? That's the shape. You have 4,255 elements, in so rows and 2 columns. And then if I add this index, if I use bracket 0, it says, well,
sorry, Daniel, we're having trouble hearing you again.
Okay, sorry, 1, 2, 1, 2. Can you hear me?
Yeah, sounds good.
Okay, all right. So, and then because it's 0 indexed, we'll add this -1, and it says, right, that value is this guy here. So what this is saying is, go to the last index value and print it. And if you go to that last index value, this is what we have here. It will have, for the value, yes, it will have a 1, and for the value, no, it will have a 0. So this is telling us that that last element is a, yes. Okay.
So we're changing the labels here from being strings to being sort of binary encoded versions of those strings. So is that right?
Yes. And
so would the network
right.
still run if we had the labels as strings, or does it only run if we have them encoded like that?
Okay, the way this network runs, it uses the output needs to be a so-called one-hot encoded vector. And the way this one-hot encoded vector works is if you're predicting 2 classes, one of the classes, if the output would be one of the classes is the true label is 1 and every other would be 0. So if you were predicting 30 labels, the output for, say, the word 2, if it was one of 30 words, in this case, you'd have 30 elements in this array. And if 2 was the first, it would be 1 saying that the value for this audio file is 2. And every other of those 29 labels would be 0. And the name of that vector in machine learning neural network speak is a one-hot encoded vector. And that's what we're seeing here. It's a vector, and it happens to be called a one-hot encoded vector. So does that explain it?
Yeah, great. Cheers.
Cool. Okay, so next we're gonna look at this. We're just going, this is a sanity check, right? We don't need to work to run this. So for any latecomers that turned up so far, we do need to run cell 2, we do need to run cell 3, we do need to run this 5 and everyone after it, and up to here, split the data. So we're just a couple of cells before that. But what we're gonna do now is just convince ourselves that what we had before up here, what we were doing here is we were opening a file and say, okay, open that file and plot it. And here we have the plot. Now what we have down here is just a slight difference as a sanity check to say, okay, we've done all this processing and we've added all these. Now we have these lists with all the data. So what happens now? So if we get the first element of OWave, and then we need to use this ravel function that will put it in the same format it was when we first loaded the audio file. That's all I'm going to say about this ravel function, but it's important to remember that we do have to apply it. And then when we run this guy, there we go. We have the same plot again, but this time we didn't load it from a file. We loaded it from the arrays we have. So we now have all that stuff that was on disk, all those files that we downloaded, now we have in memory. And that's what's happening here. And if we run that,
Yes.
same again, we'll get the audio for yes and no. Where are we? Here. Okay.
No.
Right. Now, these two, just for as a sanity check, now this guy is essential. This is a super essential bit. I mean, every bit of code is essential, but this is easily overlooked sometimes. We need to reshape to turn, we need to reshape this guy. Reshape the 2D array to 3D since the input of the conv1D must be a 3D array, right? This is incorrect, actually. No, this is a typo from the previous when we were dealing with 2D. What we need to do here is change this guy, this 1D to a 2D, because when we're actually feeding this to our neural network, we loop. We give Keras a list and say loop through all these guys. So it goes the first element, and from the first element, it gets an array that represents the file. I'm not going to go into any further detail, but we need this basically to say just add a further element here so we can actually loop through all those files. And then next thing, we're going to split the data. So here we're going to split the data between a training and a validation set. And we'll see about that in a minute. So we'll say, and the key number here is that one there. So if we run this guy, it will say, we don't see any output, but what it's saying is get a random 70% of our waves and labels and assign them to this training set and the labels to this X values and get the 30% and assign it to this Y, X and Y, so data and labels, and get the 30% and assign it to our validation set. So Y train, Y value. So now we can create the model. And this is the bit where we're actually going to start creating this thing called a convolutional neural network. So is everyone up to this point in the workshop? 1, 2, 1, 2. Can you hear me?
Yeah, fine, Daniel. Yeah, looks good.
Okay, cool. So what is this thing going to do? It's going to create a convolutional neural network. So I'm just going to quickly look up what a so let's look at AlexNet. Images. So you've probably seen this already. And we have here in this AlexNet 1, 2, 3, 4, 5 convolutional layer. No, sorry, is it 1, 2, 3, 4, 5? It's 1, 2, 3, 4. Yeah, 5 convolutional layers and 2 fully connected layers plus the output, which is 1,000. So here, instead of yes and no, the actual output that's being trying to be predicted is our 1,000 images. So we would have in this case that one vector encoding with one of those values being 1 and the 999 being zeros. So that would be the label in this case. So convolutions. This is in the domain of digital signal processing. I'm not going to talk a lot about it, but what's just the intuition is, in this case, you start with an image, you have a kernel, the first kernel here is 11 by 11, you kind of scan that image, and as you're scanning, you're performing, on every time you stop, you perform a convolution, you convolve the signal, so you end up with a value for one of those squares, and you move on, go on to the next one, next one, next one. And what happens over time is this image starts to shrink. So here it was 224 by 224, the input layer. Now here we have feature maps. So it's the image again, but every time you use a kernel and you convolve over those 3 channels, R, G, and B in this case, red, green, and blue, you end up with one feature map. And here you end up with 48 feature maps. And then we do another convolution here with 5 by 5 kernels. We end up with 128 feature maps. By the way, this 128 is because we determined that we would have 128 kernels here. So as a result, we end up with 128 feature maps. And then here we end up with 192 kernels, 192 feature maps, because we had 192 3 by 3 kernels, and so forth, until the last layer is 13 by 13. So as we perform these convolutions, depending on the so-called stride, how we're skipping as we're pushing these filters along, and how big the kernel is, we end up with these geometries. And then here we have a dense, fully connected layer, which is basically a number of units. So we can think of these as the neurons or that are inspired in models of the human brain. And here we would have 2048 and 2048. And then finally, we'd have these 1,000 neurons, which would be our output class. So in this case, they did it in 2 channels because they were using 2 GPU cards. This is from 2012, by the way. So this is like 9 years old now and was groundbreaking in its day. So if you come back to this guy, what are we doing? We're saying, right, we'll run this. And we're saying, we're going to use these libraries. We're going to import the dense bit, which we'll need to create this dense layer over here. And then we're going to import this dropout because we use, it's a technique to train neural networks where we're going to get rid of some units arbitrarily. And it's said to improve training. So, and that's all I say, but remember that keyboard dropout, we're going to use flatten because it's a common procedure that once you get to this stage here, for instance, we have 128 feature maps that are 13 by 13. How do you then go on and say, right, get all these values and do some kind of transformation and pass them on to these guys over here? So what you need to do is you need to flatten this. So you get every one of these feature maps 13 by 13 and line them up. And you end up with this long list of numbers and you feed them into these guys. So in this case, you ended up with 2048 units that are receiving the 2048 values that corresponds to 128 times 13 times 13. So that's what the maths here. So we go back here. Okay, so that's a flattened bit. Convolution 2D, we need to implement our convolutional layers, which are these guys here. So convolution 1D, sorry, in our case. And then input max pooling is another technique used here. So at some between layers, you can say, well, let's look at a section and get the biggest value for that section and move on to the other one. Same thing again, move on to the other one. So it's another kind of filtering, if you like, technique. So we're going to import model. We're going to import these two libraries, early stopping and model checking. We'll see later on where that is. And then, okay, so what happens next? We say the input is going to be 8,000, and that makes sense, right? Because that's the size of our input signals. And we say we're going to create a convolution 1D. So padding value. So it's an 8 kernel, 8 long, and it's 13 long. And I don't remember by heart what the two figures are in convolution 1D. It's so sorry, I'll owe you that one. But the key thing here is that, so we're max pooling, we're dropping out on every layer. And at the end, we'll end up, once we've applied, we've created our convolution 1D, and we flattened it. We've created a dense layer with 256 units. So what that means is, by the time all these convolutions were applied, we ended up with 256 values. So we had 8,000, and somehow that turned into 256. So we can, this is where our feature extraction is happening. We say, okay, we picked up all these values we had, and then we have two densely connected layers. So we're at this point now of the architecture. And then we say, right, we're going to have an output now, and it's going to be the length of the labels, which is 2. And the activation is going to be softmax. What that means is this is actually going to produce a score for yes and no. We're going to get that score, and the score could be any arbitrary value. It could be greater than 1, less than 1. But what this actual softmax function is doing is it's scaling those scores such that the sum will be equal to 1. So you could see it as a probability. And it makes that easier to deal with the threshold, right? Because if it was any number like 8 and 15, so it says, oh, the score for no is 8 and the score for yes is 15. What's the threshold then? Well, and maybe 10 would be a good threshold. But what if one was 1 and the other one was 3? Oh, in that case, the threshold would have to be something else. So what this is doing, this normalization, is making our life easier from that perspective, because then we can say, if it's going to be between 0, if we know the sum's going to be equal 1, we can say, well, if one of them is more than 60%, we're going to say that guy is yes, and the other one is no, and vice versa. And we'll see that in the results further down. So that's the reason we use this softmax function. Then if we go on, we have a model, the model in numbers, and it's saying, right, your input was 8,000. By the time you've done your 1D convolution, this is the length of your input now. 8, and you have 8 kernels, which is, I think what that, so, oh yes, those, okay, 8 kernels, and the filter is 13 in size. Okay, yeah, got that now. So that's what that 8 is. So 8 kernels, 16 kernels, 32 kernels, 64 kernels. And the result, we end up with 8 feature maps, 16 feature maps, 32 feature maps, 64 feature maps, and then the number of parameters. So I'm not going to go through the maths, but here at this point we have 112 parameters. At this point we have 1,400 blah parameters, and if we sum all those parameters, we end up with 1 million and so many parameters. So what does this mean? If we look at a classic X, Y, dogs, cats graph. So how's the audio there? Is that still okay?
Yeah, it's fine,
Yeah,
Daniel. Yeah.
Okay, so let's think about this case here, right? So we're trying to distinguish cats and dogs. So a scatter plot of cats and dogs. And if we said, how could we separate these two classes so such that we could say how that, well, that's like painfully obvious, right? We just draw a straight line right there. And then if we get the equation, the line equation, we'd have a slope and an intercept. So it would be in the form y equals mx plus b. So this would be a negative slope. So m would be negative, and the intercept would be up here, would be positive. So maybe 9 or 10. And that would give us a line equation. So in this case, we would say, oh, that's easy. That must be a negative 2/3. I'm guessing, right? It might be slightly different. Negative 2/3 would be m, and the intercept would be 10. So what we've just done there, just by saying y equals minus 2/3 x plus 10. Okay, welcome back. Sorry, we're quite deep in now, but there's YouTube. You can follow it there later, but you're welcome to carry on. So what happens here is we've just by guessing what those things are, we worked out the parameters, right? Y we don't worry about because Y, the parameter there is normalized, because if we multiplied, if we said 2y plus and multiplied the slope by 2 and the intercept by 2, we would just scale that line, but it would be the same if we normalized it on that y parameter. So if we say y equals mx plus b, if we worked out the m and the b, what we've just done here is we worked out those two parameters. And this is a fairly straightforward problem. We're going by a whisker length and near pointedness parameter in this case. Now, if you go back here, we have 1.6 million parameters. And imagine trying to work out what those 1.6 million parameters, what the optimal values for them are, is it's a challenging task that has been solved over decades of research. It is a beautiful story. I'm not going to cover it now, but it is a beautiful story. And what we're going to do next is we're going to compile this model. So we're going to run this guy, and we're going to define a loss function, an optimizer, and the metrics. I'm not going to run over this now because we're starting to run out of time. And then next thing, we're going to set the early stopping and checkpointing to say, yeah, when we run this, we want to stop. If it's good enough, we're going to set a patience of 5. So it doesn't get any better after 5 epochs of training, stop. And then, okay, so that's all I'll say about this. And next thing, we're going to train the model. So we go and say, right, model.fit. And this, so all being well, we're training. We're going to train over 10 epochs, and that should be fairly quick. So here we are. We have a trained model. So what happened in these 10 seconds is that the library we're using went and worked out what would be the best values for those 1.6 million parameters, which sounds quite crazy. And I think it is, because in that case, we figured, okay, that those 2 parameters we could figure out quite quickly. But this 1.6 is quite crazy. And as I said, you know, it's a beautiful story of how this back propagation algorithm, which a few of you might have heard about, was, you know, evolved over time, and then how people worked out convolutions were good for processing images, and how those two got together, the idea of a convolutional neural network plus the back propagation algorithm to find these optimal trainable parameters. And here we have it. We have a trained model. So next thing, we're going to save that model. We can save a model. And next thing, we're going to list it, verify that it is there on disk. And it says, yeah, there it is on disk. It's 19 megabytes in size. Cool. So next thing, we're going to plot. Hello? Is the audio still okay, Ben?
Yeah, it's fine, Daniel.
Yeah.
I'm just going to talk about the training just a second longer. So
Okay.
So for each epoch there, from my understanding, it goes through all of the weights of each layer of the neural network and adjusts them to find the optimal value. Is that correct?
That's correct. So
Okay.
for every time we go through a batch, we're going through a batch of 32 audio examples, and then we get a batch of the validation data and the training data. Yeah. And then the first time it's gone through, it took 2 seconds. It said, right, the loss on my first second, which is this categorical cross entropy. I'm not going to go over it now, but it's something we use with classification tasks, which is what we're doing here. And another task would be a regression task. If we were trying to predict the continuous values, for instance, imagine temperature. Given all these parameters, what's the likelihood that it's going to be more than 10 degrees tomorrow? So that would be a regression. I'm sorry, what would be the temperature tomorrow? That would be a regression problem. We're trying to predict a continuous value. So it's going to be 10.5 or 10.6, etc. So back here, that's the loss function we're using. And the first time it went through, that was the accuracy. So how well it was predicting, and that is for the training data set, which is 70% of our split. And that one is for the validation data, which is 30% of our split. And 10 epochs later, it says, right, the loss at this point is that value, and the accuracy is 0.95% for the training data set. And for the validation data set, it's gone up a little bit, and the validation accuracy it's lower a little bit. So if you plot those two, so let's plot this to see what it looks like. It says, right, up to 8, those two were quite close, but when it came to the end here, the test loss, which is in orange here, started to increase, and the validation loss was still decreasing. So at this point, I'm just going to drop the keyword. The keyword is overfitting. So if these two values start diverging, we would say, the model is beginning to overfit here, because even though the training is still kind of improving, the test loss is starting to get worse. And then at this point, you would say, right, this is a technique, and it's called early stopping. That's what we defined up here. We said we want to use early stopping if it wouldn't improve after 5 epochs. So, sorry, that's in this case, right? What we did here was we said we're going to stop after 10 epochs. So what happened here was we stopped after 10, and we did notice that there was this divergence going on here. So perhaps it was a good time to stop. And there's a big discussion around that. When should you stop training your model? So now we're going to load the model from disk. We wouldn't need to, but we're doing it because it just shows us a practical aspect of machine learning, artificial intelligence. If someone said, oh, by the way, I developed a model here to do some audio predictions, say, oh, have you? Can I borrow it? And then, yeah, there you go. And there's your model. So if we had done nothing, and from this point we said, okay, let's load this model and make some predictions, we could have started from here, load the model. So next thing, let's make some predictions. So we define a predict function, which will output a probability and the classes. And as an input, we'll take an audio array. So all good till here?
Yeah, all good.
Okay, cool. So now we're going to make a prediction. So we do need to run this guy to make sure we have this function definition in memory. And then we're going to run a random prediction. So what this guy is saying is, get a random index value up to the number of the training examples I have, and then print the selected index, which was 83, and then print the selected audio. So it says, show me the class name of this audio thing you selected. And it says Oh, it's a no. You selected a no. Okay, now go and run that prediction and tell me what the prediction is. And what the prediction is an array, and it says, okay, so for this array, what we have is for the first value in the array is 0.99. The second value in the array is very close to 0. And the sum of these two values is 1. So what this is telling us is the likelihood that it's going to be this first label is greater than it's going to be the second label. And the predicted class is no. So we run this guy. No. And in this case, it did work. Sometimes it doesn't. So if I run this several times, so this time it worked as well. It says, right, the selected audio is a no. The predicted class is also a no. No. I'm just going to run this like 5 times quickly to see if I can pick up mislabeled prediction. Okay, I failed to, sometimes it works, but this model seems to be doing okay. So the next thing you'd ask is, okay, so what's a practical application of this thing? We have a yes and a no. The model can predict a yes and a no. So as an example, let's look at something we could do, a practical application. Let's say we had an audio capture, and then so there's a to-do here. We would have to capture the audio. Then there's another to-do is we would have to pre-process the audio exactly as we process the audio to train this model. And this is key, because if someone just gave us a model and said, oh, here's my model, and no other information, that wouldn't be of any use to anyone, because you need to know how the data is pre-processed, what's being presented to the model. Is it a 1D convolution? Is it a 2D convolution? Is it something completely different? So that is information we must have if we're borrowing a model from somewhere else, or if we're running our own models. It's something we must not forget. And then we say, right, if the predicted class is yes, and there's another to do here, there's a hardware implementation that's missing. We need actuators, something opening and closing a door. And then if we run that, it would say doors opening. Okay, and same thing again, if we run that guy and we had a no, so let's say we said no to our model, right? So in this case, I just picked out a random example. And then if we then put this through our door opener and we'd say no to it, it would say, okay, door's closing. So that would be a practical application of what we could do with our neural network. And okay, so that's all well. We know that we do need to pre-process the data, etc. How do we get a hold of this model? We could do it with these 2 lines of code which you have there. So if I run these 2 lines, it will download the model, and it might take a little while, but that's the model downloading. Other practical considerations. So let's say we say, okay, we're happy with this model. We trained it on the Google Cloud. Oh my God, I forgot to tell you guys about the GPU. Ben, did that thing work okay?
Don't worry about it, Daniel. In the notebook, it automatically enables the GPU.
Oh, fantastic.
Yeah.
Oh, thank God for that. Okay. Otherwise, okay. So,
yeah, I double checked it. Don't worry.
Okay, cool. Thank you. Right. So practical considerations. Let's say we've trained it on Google. We're happy. We're clued up on this pre-processing bit that we do need to pre-process the audio file. We do need to reduce sampling rate before we give it to our neural network. It would have to be a second long. It would have to be 8,000 samples. So at this point, what else? There's one last thing we need to watch out for. And that is that the versions for Python, Keras, I'm not going to save this, but this is the last practical this is the practical consideration. So if you run this, it would say the version of Python you're running up here on the cloud is 3.6.9. The version of TensorFlow is 2.4.1, and Keras is that one there. So what's that mean? If you now look at those 3 libraries, where you want to run this model, they would have to at least match, but not be lower. If they're lower on the library you're transferring this model to, I think it's very unlikely to run. I've had these problems like switching models between servers, and then like I was using the Intel cloud to train models for my dissertation. Those ones were okay. And then I was using the City cloud to train models, but those ones are not okay. And then in the end, I worked out, the problem is this guy here. But by then, it was, anyway, so that's it. Thanks everyone. And any questions?
So one way of getting around the software issue there would be to put it in a Docker container or something, wouldn't it? So you can completely control all the software.
That's one way of doing it. But another thing that Python allows is it allows you to set the versions. So if you have more than one version, or if you were missing this version, you could say, right, I want to download this version and I want to use it. And also you could use virtual environments in Python, but yes, you could use a Docker container. But that's the one thing to be aware of, that those versions would need to match.
Mm-hmm. So just for everyone else, the reason why we were worried about the GPU earlier was in our practice for this session, we found that running it without a GPU enabled increases the amount of time it takes to train the model by a good few minutes. Yes. So I don't know, Daniel, if we were able to demonstrate the change, like if you're able to change the runtime type on your notebook and show them how long it would take if you just use a CPU. Is that possible?
Okay, we can do that. Yes. The one thing that's going to happen is if we change the runtime.
Oh, you'll have to download it again.
No, yeah. I won't have to download it, but we'll lose everything that's in memory. So we're going to have to run, which is not the end of the world. It just might take a few minutes to get to the point where we could say, right, if it's not running with GPU, we could then see that it's running.
Okay, yeah, that's slower. Fine. So yeah, the point is that models train a lot faster on GPUs. Are you able to explain why, Daniel? Because I can't.
With GPU?
Yeah, why is the GPU help?
Okay, one sec. Just before we go there, I just want to answer a question here that Russ is asking. So Russ, the question Russ is asking is, can you save a model during processing if you have a lot of files? So the question now is, if we want to save a model, we want to get this thing that we have in memory to disk. And so we demonstrated the procedure, right? So, okay, we can say, yeah, save the model as we did down here. So model save. Now, the question is, have we got enough space on disk to save the model that we have in memory? So now that would be the next thing we would have to look at. And Russ, earlier in the Jupyter Notebook, we had a list of commands here. So getting to know the environment. And one of them is this guy here. How much space have we got? So if I commented out this line, so this is first up there right at the top, and I'm uncommenting that line just by removing that hash sign. And if I run this guy, it will say, oops, what's going on? Don't want this one because it's too verbose. Run that guy again. It will say, you have 34 gigabytes available. So there's plenty of space because our model is, if we list what we have on disk, so uncomment that last line, it will say, where are we? List, here we are. And we want to list, sorry, we don't want to list, we want to list our current working directory. And we want to see the size. So I'm going to say list size in human readable format, LSH. So I run this guy and it says, right, that model of yours, it's 19 megabytes in size. So at that point, addressing your question, can you save a model during processing if you have a lot of files? So I don't quite understand what the during processing bit means, like if the model is being trained, but yes, you can save a model as you're training it, like save the best model. And then once it's trained, you can save it to disk, provide you have enough space on disk. And here we have plenty of space. We still have all that space. and the model is much smaller in comparison. So from that perspective, yes, you could save that model to disk. Okay, there's another question here. Usually if the data set is small and the model parameters are not that high, you will likely see better performance on CPU. Otherwise, GPU will perform better. Okay, so that's Bernardo answering the question. Thanks for your for your help in answering that question.
Yeah, Daniel, can you also show the way you change from CPU and GPU in the?
Okay, yeah.
Maybe
So
just
to change from CPU to GPU, where was it? Change runtime type. So up here at the top, we have this menu. We have change runtime type. Ah, I am on GPU, bless. Okay, good. So I don't remember changing it myself, but as you said, Ben, perhaps at some point when I was running the code, it changed itself. So let's change this guy to none. Okay, so basically what would happen here is if we're running on CPU, this training would be a lot slower. So when we'd get to this step over here, it would not run. That's what I experienced when I was training this model. So the time now is 7 minutes past 7. And what you guys reckon? Any more questions or any closing comments, Ben, Max?
Yeah, I guess if we'll be around for a few minutes if there is more questions in the chat or in the voice chat if you want to ask us.
Yeah, I'm around. Yeah, I'm not in a.
Yeah, but generally, thank you for the event, Daniel. It's been really interesting. I think lots of people learned new stuff today, which is amazing. So yeah, and
yeah, thanks, Daniel, for putting together the notebook and everything. We appreciate it.
Cool, no problem. Thanks, everyone, for turning up.
Cool. So as we said, it will be on the YouTube page that we put in the chat a couple of times. So keep an eye on that. But you can follow us on Instagram or Facebook or anything to keep up to date with our other events. Cheers, guys.
Yep. We'll send the link in the chat for social media as well right now.
Okay, I stopped sharing there. So do I need to hand it over to you, Max, or
yeah, I think it's fine. It's fine for now.
Okay.
Should we wrap it up?
Yeah. Yeah. Okay. Okay. Then so hopefully catch up soon again. Run another workshop or two and keep going.
Yeah. Yeah. Stay tuned for future events. But yeah.
Cheers. Bye.